This is my Calculus 1 course. Today we're going to learn some more applications of differential calculus, specifically optimization problems. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. There are two parts of this course that I would say are particularly intimidating. One part is the related rates problems that we did previously, and the other part is what we're about to do today, optimization problems. And the reason that these problems are so intimidating is that they're word problems, and it's not exactly obvious how to solve these problems. Each problem takes a significant amount of thought and time to solve, and so this part of the course can be, like I said, intimidating. But we're going to start off with some pretty basic problems here, and a lot of the problems that we do today are going to be very similar to each other, and that's for a reason, because I want you to not have to worry about doing a lot of variety of problems when you first learn how to do optimization problems. I just want you to learn the process that we're going to solve these problems with. And then in the next class, we're going to do some different types. We don't have time to do every single type of problem that you can see, so I'm not going to give you, 30, 40 different types of problems, because we just don't have time to do that in this course. The most important thing is that you know the basic idea. So here is the procedure for solving optimization problems. Like the procedure for related rates problems, there's 4 steps. And the most important thing that I can tell you today is that you need to stick with these 4 steps. When we learned related rates problems, I told you that if you did not stick to those 4 steps, then you would just be completely lost. And that's pretty much the way it is with optimization problems. You need to stick to these 4 steps. These steps are your lifeline. They are your salvation. If you do not use these 4 steps, then you're just going to sit there and stare at the page and get nothing done. Is that clear? You need to stick to these 4 steps. Let's try one. And if I didn't give you a chance, go ahead and take a picture of those steps. So it says here, a man wants to create a rectangular enclosure next to the 40-foot long wall of his building by erecting 56 feet of fencing. He needs only 3 sides of the enclosure because his building will serve as one side. Find the maximum area of the enclosure that can be produced in this scenario. So again, it's not exactly obvious how we should solve this problem. But you're going to see that if you have your steps in front of you, it's really not that difficult. I'm not going to lie to you, these are pretty intimidating and challenging, but if you follow your steps, then at least you have some sort of a guide. So first we're going to draw a picture. So this guy has a building, and apparently the building is 40 feet long, and he's going to erect a fencing that's going to be in the shape of a rectangle. And obviously this side of the enclosure cannot be longer than 40 feet, because then it wouldn't be an enclosure anymore. For example, if you did something like this, well, you've got green, or I should say, you got blue gaps in the enclosure, right? So that can't be. So we have some restrictions on this picture. Okay, so now we've got some variables involved. We can change this length based on how we want to design the enclosure, and we can change these lengths. So this is step number 1, is to draw a picture and label variables and constants. We have a constant, which is 40 feet. the building is 40 feet long, and we have variables, the dimensions of the enclosure. So that's it. We're done with step number 1. Step number 2 is to write an equation of the thing that you're trying to maximize or minimize. So we're trying to, it says here, we're trying to find the maximum area of the enclosure that can be produced in this scenario. So we're trying to maximize the amount of area that we'll have. So that's this blue area here. Now, obviously that's a rectangle, right? So what is the area of a rectangle? Well, length times width. But we're using the variables y and x. We could put L and W here instead if you really wanted to. There's no reason that you couldn't do that. But I'm just going to stick with y and x. Now, the second step is often the most difficult step because we cannot write our orange equation with more than 2 variables. We need a dependent variable and an independent variable, either x or y. You can choose which one you want, but we can't have 2 variables over here. We only need 1. So this is very different from the related rates problems that we did. You need to understand that the steps are very similar, but the process is going to be significantly different. So be aware of that. These problems aren't going to be exactly the same as the related rates problems. So what we have to do is we have to use additional information. And that information is going to be given by this stuff here. It says the total length of the fencing is going to be 56 feet. So the perimeter of that rectangle is 2W plus 2L, right? That's just the, that's the definition of the perimeter of a rectangle. Now we know the perimeter. Well, first of all, let's point out that we don't have one of the lengths because remember this side of the fence, it's not going to be fencing, it's just going to be building. So we only need 2W plus L. So we're only counting this x, and this y. Because it's talking about how much feet of fencing we have. Again, this pink side here of the enclosure is not fencing, so that's not included in the 56. Is that clear? So we don't need 2L, we just need L. And the perimeter is 56. That's how much fencing we're using. That's 3 sides of the rectangle. Now, and I'm going to put a cross through that just so we can understand that we changed that based on the context of the problem. Now the width is x. I just chose x, and the length is y. So now we have an equation that we can use to put our expression, or our value that we're trying to maximize, a, in terms of only one variable. So I'm going to solve for y. And then I'm going to take this expression here and I'm going to plug it in for y. And I'm going to write a in function notation. Well, I guess I can do that in the next step. So I have 56 minus 2x times x. All right. So now I'm going to write the area as a function of x, and I'm going to distribute, and I get 56x minus 2x squared. So do you see how things changed? Up here we had 2 variables on the right side of the equation, but now we only have 1. Okay, so now at this point we're done with step number 2. So again, that's kind of a lot of work to have to deal with that. Like I said, oftentimes that's the most difficult step. But also be aware that sometimes students make mistakes in the first step, and that's really not good, because if you make a mistake labeling constants and variables, that can mean that you'll definitely get the problem wrong from the very beginning. Okay, so now we want to figure out the maximum area. So do you see this orange area, a of x? We're trying to maximize that value. Now, to be honest with you, this purple expression here, you might notice that that's actually just a parabola. If you graph that out, it's a parabola going down. So obviously the y value of the vertex, which is going to be this area here, that y value is going to be the maximum area. So we don't really even need to use calculus. We can just use our knowledge of, quadratic expressions. This is a quadratic here. So we don't really need to use calculus. We could just say, well, we know that the x value of the vertex is negative b over 2a. You may recall that from my previous courses. So we calculate this, and then we plug that in, the x value of the vertex, to get the y value of the vertex, and then we have our maximum area. So we're done, right? But this is a calculus course, and calculus makes things easier, so why not use the calculus? We want to practice our calculus, but we also want to make things easier for ourselves, so the calculus does that. So the third step is to find the derivative of the expression. So there you go, that's the derivative. The fourth step is to use the derivative to find the maximum area. Now again, if you have a parabola, the derivative is the slope of the tangent lines. So if you want to find the slope of the tangent line when x is equal to whatever this x value would be, you just plug it in, and then you get the slope of your tangent line. But the slope at this point, the slope of the tangent line at that point, is going to be 0. That's where you find the maximum value. So we want to set the derivative equal to 0. Now it's also possible that a maximum value could occur when the derivative is undefined. But as you can see, there's no place where the derivative is undefined. If you're wondering when that would happen, that would be when you have like an x in the denominator of your derivative. Then in this case, if x is 0, then the derivative would be undefined, so that would be another point we'd have to check. Again, we want to check all the critical numbers. Those are the possible places where the area could be maximized. It's also important to keep track of the endpoints of our domain of the function, but we'll talk about that later. There's a lot of things going on here, so I know that this is kind of intimidating, but again, you just have to do your best here. And most important thing is to follow these steps. Again, you're probably thinking to yourself, this is really overwhelming. I don't know about this. Well, if you have these steps in front of you, then that's your anchor. That's how you remember how to do all this stuff. So that's going to be 14 if we solve that equation. And this is 14 feet. I don't think it's really necessary to write units at this point, but we just want to be sure that we understand what we just found. So this is actually the x value of the vertex of the parabola here. So now we rewrite our, well actually we know we have a quadratic, so it's not really necessary to check that this is a maximum or minimum. But technically, remember, you always have to use your first or your second derivative test to check to see if this is a maximum value or a minimum value. But because we know that this is just a quadratic, and if you graph it as a parabola, we know that that's obviously going to produce a maximum value. So just for time's sake, we're not going to use the first or the second derivative test right now. So we can just go on to the last step. Now we do want to consider the domain. This is another thing. And by the way, a lot of students just don't use the first or second derivative test. They just assume that this is the value we're looking for, and they just plug it in, and they're done. And in most cases that actually works, but technically you're not really supposed to do that. You're supposed to use the first or second derivative test to determine if that's actually a maximum, the location of a maximum or a minimum. The second thing that students often don't do is they don't consider the domain of the function. This purple area function actually has restrictions on it. There are certain x values that cannot exist. So what is the domain? We're definitely going to look at that because that really matters. We want to make sure that this 14 is actually in the domain. If it's not in the domain, then we're in big trouble. So what is the smallest value of x? Well, actually, let's start with the biggest value of x. This is something where it's not easy to think about this. So if you have a little trouble with this, that's okay. It's totally normal. But let's think about the restrictions on x. If you make y smaller, then that means x is going to get bigger, right? Remember, you only have so much fencing. So if you change y, then x has to change. If you make y smaller, then x would have to get bigger, right? If you make y really, really, really small, then you might have something like that. So this would be x, and this would be y. So x is getting bigger as y is getting smaller. And the reason for that is you're definitely going to use 56 feet of fencing. But if y goes all the way to 0, what would be x? Think about that. If y goes all the way to 0, what would be x? You might say, well, x would be 56. Well, remember, there's two parts to there's two x's. There's the top part of the fence and the bottom part of the fence. So it would actually be 56 divided by 2. That would be what x would be if y actually approached 0. X would approach whatever 56 divided by 2 is. So again, I know that might be a little hard to see, but again, if you make y smaller, then x will be bigger. And if you keep making y really, really small to the point where it approaches 0, then x would actually approach whatever 56 divided by 2 is. So that's why these problems are considered to be so difficult, is because it just takes a lot of thought. Now again, a lot of students are just going to skip the domain and say, well, I don't really care about it. I'm just going to assume that this purple 14 is in the domain. But we can't really do that. You're not supposed to do that, and they're not going to really let you do that on the AP exam. You're going to be expected to consider these things. Now, we found the biggest value of x, and that's going to be, looks like 28. What is the smallest value of x? Well, let's say that we want to make y bigger. Well, the biggest we can make y is this length here. Because, remember, if it gets any bigger, then you're going to have gaps in the fence. See these yellow gaps? Y has to, it can't be bigger than 40 feet. Because then we're not going to have an enclosure. So the biggest value of y is actually 40. Now think about this. If y is 40, then what would x be? So go over here. If y is 40, then what would x be? So the total length of the fence is 56 feet. So if y is 40, that means you have 56 minus 40 feet left, right? And remember, you have to divide the fence, or the part of the fence that's x. You have to divide it, that leftover part that's for x, you have to divide it by 2, because there's 2 sides to the fence. So that's going to be 56 minus 40 divided by 2. I know that's pretty complicated stuff, but again, these problems they're intimidating. So 56 minus 40 divided by 2, and that's going to be 8. So the smallest value of x is actually 8, and the biggest value is 28. So now we know that this critical number here is in the possible domain, so we just want to make that clear. Now again, the problem wouldn't be possible unless that were true, and for that reason a lot of students just skip the domain. They don't care about the domain, and they don't care about the first or second derivative test. But as your teacher, I can't do that. I'm not really allowed to do that. Okay, so now we're pretty much done. Now we're going to take this purple equation, and we know that this is a maximum value because we know the graph of that function. We know that whatever y value we're going to get is going to be the y value of the vertex, because 14 is the x value of the vertex. Alright, and don't be afraid to use your calculator to find the value of this. You should know how to use your TI-84 Plus or whatever calculator you're using pretty well by now. So what I get when I enter this into my calculator is 392. So that's it. That's the maximum area that we get, and we're done with the problem. So just keep in mind that it's going to be a lot. You don't have to take that much time to do this problem. It can potentially go faster for you because you're not going to have to explain it to somebody, you know. So don't be discouraged that took kind of a while. Now, if we write this as our final answer, we're going to get points taken off. Do you see why? We forgot something. What are the units of area? We just found the maximum area. The units of area in this case are square feet. All right, so there you go. Okay, so I'm going to give you a chance to take a picture again of those steps, and let's try the next problem. This problem is very similar to that problem we just did, but it's a little different. Okay, so a shepherd wants to set up a rectangular enclosure for his sheep. He wants to use 100 meters of fencing, and he needs 2 compartments, picture below. Find the maximum area of the enclosure in this scenario. So now we've got compartments. Now don't worry, it's not going to be that much more difficult. Step number 1 is to label the constants and variables, and in this case we're only going to have variables. So y, 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 x, and x. Now the reason that we have 3 y's is because, again, each part of this enclosure is going to take up fencing, right? It's going to be part of the fence. So we need 3 y's. Okay, step number 2. We're going to find an equation of the thing that needs to be maximized, or an expression that represents the thing that needs to be maximized. So we're maximizing area, and again, obviously the area of a rectangle, the area of this whole enclosure is length times width. But we're going to use again x and y. Now we have a problem. We have two variables. We're only allowed to use one. And by the way, notice that we didn't have any DTs. We're not using Leibniz notation, and none of these variables are in respect to time. I should have mentioned that. When we found the derivative with related rates problems, we had things like dx over dt that popped out, right? That doesn't happen with this, because x is an independent variable. It doesn't rely on time. Think about it. What does this problem have to do with time? Nothing. Is that clear? There's nothing in here that says anything about time. So you have a dependent variable that is dependent on x. So you do have one variable that's dependent on x, and if we use Leibniz notation, we would have to, when we take the derivative of that pink variable, instead of writing as a prime, we would write it as dA over dx. So you could use Leibniz notation, but typically it's not used for these types of problems. So I want you to be familiar with the way it's usually written. But when you find the derivative of the other side of the equation, you're not going to write, again, dx over dt. X is not dependent on time. X is dependent on nothing. It's an independent variable. You really need to understand that that's how these problems are different. If you don't understand that, you're going to have some big problems. Now, how are you going to make sure that you don't have problems? Just do practice. Practice problem after practice problem after practice problem. That's the only way to understand how to do these. So we have two variables. We're not allowed to have two variables on the right side of the equation. So we're going to add up all the parts of the fence. And in the previous problems, we wrote perimeter of a rectangle is 2w plus 2l. But as you can see, this is really a different situation. So that formula doesn't really do much for us. I'm just going to write what is pretty obvious, and that is that the length of the fence, which we know is 100 meters, is 3y plus 2x. You're adding your y's, that's all these pink y's, you're adding those with the yellow x's. There's two yellow x's. Do you agree with that? You're adding that up. That's the total length of the fence is 100. So we're going to use that equation to help us convert our area expression so that it only has one independent variable. So I'm going to solve for y. And I get that following expression. And so also I want to make it clear that I got that 100 from there. So now we have a is equal to 100 minus 2x over 3 times x. So I plugged in all that. Maybe I should make that green because I made it green before. Plugged in all that there. Now, we don't want to keep it in this form because then we'd have to use the product rule. We don't want to do that. So I'm going to change this to function notation. And I'm going to first change the green expression. And I probably should have done that over here. In fact, yeah, I'm just going to change that over here first. And I'm going to just plug that in. So we have 100 over 3 minus 2 over 3x. I'm going to plug that in. Again, there's a lot of different ways you can do this. So if you're doing it a slightly different way, that doesn't necessarily mean it's wrong. But of course, you do have to be careful how you write this stuff. It is math. There's a right way and a wrong way to write math. Okay, so I plugged in that green expression, and I used the distribution property. And now I have, well, I'm done with step number 2. Again, step number 2 is often the most difficult step. So on to step number 3. I want to find the derivative of that expression. Alright, so I found the derivative. On to step number 4. I want to find the critical numbers, and that's when the critical numbers are x values that make the derivative equal to 0 or that make the derivative undefined. There's no x values that are going to make this expression undefined because we don't have any letters in the denominator of a fraction. If this x were down here, then that would be a problem. There would be a situation where the derivative would be undefined, but we don't have that. But there are some x values that will make the derivative equal to 0, so I'm going to find those by setting the derivative equal to 0. Now, we care about that because, again, that's where you have a maximum value when the slope of the tangent line is 0. So again, we don't really need to use calculus because we know that's just going to be a quadratic. And when we have a maximum value, the slope of the line that's tangent is going to be 0. So that's why we plugged in a yellow 0 there. So now we're going to solve. And it looks like we get x is equal to 25 if I did my math right. Okay, and that's going to be meters, 25 meters. Now again, normally we'd have to use the first derivative test to check to see if this is a maximum or minimum value. Or, to check to see if this is the location of a maximum or minimum value. But again, we know that expression represents a quadratic. It's pretty obvious that 25 is the location of a maximum value. We also know that the parabola is going down because we have a negative in front of the x squared term. I didn't say that in the previous problem, but that's something important. So now we need to figure out the domain because we don't even know if 25 is in the domain of this problem. So the domain is all the possible x values that you can plug into this purple expression, or the purple equation. So what are the smallest values of x? Well, x could actually be 0. I don't see why x could not be 0. I mean, it couldn't be equal to 0, but it could be that's one of the bounds. Now, I didn't mention up here that we don't have brackets in the previous problem. That's because you probably noticed that x cannot be equal to 8. X cannot be equal to 28. Because in those situations, well, now that I think about it, this actually should have been a bracket. This parenthesis here should have been a bracket, technically. So, again, it's kind of difficult to explain why that is, but basically, let me first talk about why we have a yellow parenthesis down there for the biggest value of x. The reason that x cannot be equal to 28 is because the enclosure would collapse. Maybe I shouldn't use the word collapse. It would there wouldn't be an enclosure. Because if x were 28, then that would mean that there'd be no fencing left for y. And so these two halves would actually just contact each other. They'd be so close together that you wouldn't have any enclosure. So it'd just y would get smaller and smaller and smaller until eventually the whole thing just collapses. So x cannot be equal to 28. But x can be equal to 8. Because that's when y is equal to 40. Remember, if y is equal to 40, think about this equation over here. If y is equal to 40, then that would mean the only leftover fencing for x would be 16 feet, because 56 minus 40 is 16. And since there's two parts, upper part and the lower part of the fencing, you'd have to divide that by 2, but it's perfectly fine for x to be 8. That just means that the fence will be over here. It will be all the way on the borders. So I need to write a bracket there. Again, there's so many details to these problems that it's kind of overwhelming for students to do this. But again, that's why you just try your best, and you keep those steps in front of you. So I was saying for this problem that x can be, well, it can approach 0. X can theoretically approach 0. It can't actually be 0 because then you wouldn't have an enclosure, right? Looking up here, if x is 0, then there's no enclosure. But x can approach 0 theoretically, right? So that's the lower bound. And then we want to know how big x can get. To figure out how big x can get, you would have to let y approach 0. Because if x is going to get really big, then the y parts of the fence are going to get really small. Because again, you only have so much fencing. You're going to use exactly 100 meters. As y approaches 0, that means that the only part of the fence, this pink expression here, this 3y, actually goes to 0. And if that expression approaches 0, because y is approaching 0, then what does the blue x approach? Well, if the whole pink 3y goes to 0, then that means all of the 100 meters of fencing is going to be devoted to the x's. Now there's two x's, right? One on the top, one on the bottom, so you have to divide it by 2. So in other words, x, the biggest value of x would be 50. Now again, that's a lot of thought that has to go into that. So that's why a lot of students just don't even think about the domain. So that would be let's see, we could write that as, I guess, 100 divided by 2. So the domain of the function is 0, 50. Now, do we put any brackets on the domain? And the answer is no, because if y goes to 0, then you don't have any, y going to 0, that corresponds to 50 for x. And you wouldn't have an enclosure if y went to 0, right? So x cannot actually be 0 or 50 in this particular example. So this just confirms that 25 is in the domain. These are things that you want to keep in mind. Now, again, we know that this is a maximum value because we know this is it's a quadratic, or it's a parabola opening downwards. It looks like this, right? So 25 is the location of the vertex. So what we do now is we plug in 25 to this expression here. So we get 100 over 3 times 25 minus 2/3 times 25 squared. So don't be afraid to use your calculator for that. And when I enter this into my calculator, I get 416 2/3 for the maximum area possible in this scenario. So 416 2/3, or you can just write 0.6 bar. That might be easier for students to write 0.6 bar. Again, in upper mathematics, We don't tend to use mixed numbers very much. We just don't prefer that. So, and that is the answer. Now again, a lot of people are going to just leave their answer as that blue number there, but you're going to get points taken off if you do that. We need square meters. Area is measured in meters, right? Square meters. So there you go. So as you can see, there's a lot going on here, and that's why these problems are very intimidating. So I want you to get a picture of all this information, and remember, this information over here is your salvation. That's your lifeline. I want you to use number 1, and also I'm going to keep number 2 in the picture, and I want you to do number 3. If you get stuck, that's okay, but you need to give it an honest attempt. Okay, use your steps, draw a picture, label constants and variables, and then continue on as you go through your steps. So try number 3. When you come back, we'll do it together. Okay, we're back. Again, that's the maximum area that is possible in this scenario. So if you got that one right, excellent. So let's just double check and make sure we have all that right. Everything looks correct. So if you got that right, excellent. So I want you to take a picture, if you haven't already. I'm just going to give you another chance to take a picture of these, or this information, and take a picture of these 2 problems. And number 2 is going to help you in particular with number 4. So go ahead and try number 4. And when you come back, we'll do it together. Okay, we're back. If you got that right, good job. Now notice that I used y. You see the purple expression? It's in terms of y. You see a prime, it's in terms of y. If you did it in terms of x, that's okay, but you should still get the same answer. Your domain is probably going to be different, and these expressions are going to be a little bit different. You may have it. You're going to have a different. You may have a different critical number. My critical number was 100. That's because I'm using y. If you used x, if you solved for y up here and put this expression in terms of x, your problem might be a little bit different. But this yellow number down here, your final answer should still be 20,000 square meters. So just be aware of that. So if you got 20,000 square meters, good job. Okay, so let's try another problem. This is a slightly different type of problem. A company wants to make a box to ship its product in. The volume of the box must be 2,000 cubic centimeters, and its base must be a square. Find the dimensions of the box that will minimize the cost of the materials used to make it. So notice now we are minimizing, we're not maximizing. So the function is going to look something like this. It's going to be a minimum value somewhere in the domain. Now it says we want to minimize the cost of the materials. If you want to minimize the cost, this problem assumes that we understand that you want to use the least amount of box material possible. So whatever you're using to make the box, you want to use the least amount of material. And the way that you measure the amount of material you're using is with surface area. So I just want to make that clear. So first, step number 1, I'm going to attempt to draw a box. most important thing is that, and it doesn't really have to be that great of a picture. You don't have to be an artist here, but the important thing to understand is that, again, the bottom of the box is a rectangle. I don't think I'm really drawing this, excuse me, the bottom of the box is a square. I'm not really drawing this that well, but down here we have X and down here we have X. And we'll call this H. So the reason that we have X's that are, the reason that those sides are both X's is because it has to be a square base. You see here, it says its base must be a square. So that's that there. Okay, so it looks like we only have variables in our picture. So now we're trying to minimize the surface area, so that's the function that we're going to write. So if you recall, the surface area of a box, which we also refer to as a rectangular prism, I'm going to make H, capital H. The surface area of a rectangular prism is given with this formula. Now, we have two sides here, and then two other sides, so there's 6 sides, and we're just adding up the area of each side, and each side is a rectangle. In this case, 2 of the sides are squares. So you're adding up the area of of 6 rectangles. So the width and the length are both X. So that simplifies our equation. And so we have A is equal to 2x squared plus 4xh. Do you see why it's 4xh? Because these are like terms. So it's 2 apples plus 2 apples is 4 apples. Okay, so now the problem that we have at this point is that we have 2 variables on the right side of the equation. We can't have that. We need only 1 variable. So now we go to some other information, and of course that information is this: the volume of the box must be 2,000 cubic centimeters. So the volume of a rectangular prism is given by LWH. And we know the volume has to be 2,000. The length, of course, is X, the width is X, and H is just H. So we have 2,000 is equal to X squared H. So now we can use that equation to solve for H. And then we plug in that expression for H up here. Okay, and so we have 8,000 over X there. So we're done with step 2. Again, as you can see, step 2 is pretty involved in many cases, most cases. Okay, so also I'm going to write this with function notation just to demonstrate that this is a function of x, even though we know it's a function. Now we're going to find the derivative. That's the 3rd step, because we're going to set the derivative equal to 0 and find the critical numbers that may maximize or minimize whatever we're trying to maximize or minimize, in this case the surface area. because we want the least cost, the minimum cost, which means we need the minimum amount of material, which means we need the minimum amount of surface area. So we're going to find the derivative, but if you try to find the derivative with this fraction in this form, then you have to use the quotient rule, which is completely fine, but I find that most students don't like to use the quotient rule if they can avoid it. So what we're going to do is we're going to change that to 8,000 times x to the negative 1 power. Do you agree with that? Are we allowed to do that? That's exponent rule number 8, if you recall, going in the reverse direction. Sorry, my computer's going kind of slow there. Okay, so now we can find the derivative. Again, we have not found the derivative yet. You see this orange expression? We didn't find the derivative yet. Okay, we just changed the form so that we could find the derivative easier. So now we're finding the derivative, and we get that expression there. Now we are going to change this into something that we actually can interpret. Remember, negative exponents don't really have any meaning unless you actually convert it to something that does have meaning. So that's what we did from here to here. Now I'm going to continue further. We want to find the critical numbers. Remember, the critical numbers are the possible places where you can have a maximum or minimum value. So we want to find the critical numbers. And the best way to do that is to combine these terms into one expression. So I'm going to get a common denominator, and I want you to be very aware that you don't have to show all these steps. And most calculus teachers are not going to show these steps for you, but I'm just trying to help you as much as I can. I can't show you every step because it would just make this class too long, but we just have to get a common denominator. This is something that you should already know. I want to make it clear you should already know how to get a common denominator and combine these terms. So your calculus teacher is going to expect you to be able to do that. So we get 4x cubed over x squared minus 8,000 over x squared. And of course that allows us to combine the terms. So we have 4x cubed minus 8,000 over x squared. Now I'm not going to show this anymore, so I want you to be aware of that. I'm showing that one time. I'm not going to do all this work again because it just takes too much time. Again, you should know how to do that at this point in your math education, how to get a common denominator and combine terms. So now what I'm going to do is I'm going to rewrite that expression up here for step number 4. And so now we're ready to find the critical numbers. And the critical numbers are the numbers, again, where you can possibly have their location where you can possibly have a maximum or minimum value. And the critical numbers are any x value that makes the derivative undefined or 0. So if the derivative is undefined, that means the denominator is 0. If the derivative is equal to 0, that means the numerator is 0 and the denominator is not 0. So we're going to see what we can find. So obviously if you square root both sides, you get 0. That makes the derivative undefined. But we don't really care about this because we're not going to let x be 0, right? that's not really in the domain of the function. Now, if you solve for x, you get the cube root of 8,000 over 4. You want to add 8,000 to both sides, divide both sides by 4, and then cube root both sides of the equation. And so we end up with the cube root of 2,000, it looks like. Now you might say, wait a second, why didn't you put a plus or minus symbol? We're supposed to do that every time we root both sides of an equation. Well, this is a cube root. It's not a square root. If you have an index, which is an even number, then you have to write plus or minus. But if it's odd, you don't write plus or minus. It's not necessary. Okay, so now what do we do? Well, this is a critical number that we really care about because that could possibly be in our domain. So let's go ahead and calculate what the cube root of 2,000 would be, because we're going to need to have an idea of what that actually is. If you're using your TI-84 Plus, I want you to push the math button at the upper left and then go down to number 4 and press enter, and then enter 2,000 and then enter. So that's the cube root. And if you have a different calculator, obviously you just have to figure out how to do that. So we get approximately 12 point, I'm just going to say 12.6. Now, in the previous problems, we had a quadratic equation, a quadratic expression, so we knew that it was just an upside down, or a parabola that opens that opens down, right? So we knew that this was a maximum value. But here, we don't have a parabola with this purple equation. We don't know what in the world that's going to look like if we graph it. So we don't know if this is a maximum or a minimum value. Now, most students, they're just going to assume that this leads us to a minimum value because the problem wouldn't even be possible. There wouldn't be an answer possible if this didn't lead to a minimum value. So most students, to be honest with you, they're just not gonna check, and they're not gonna find the domain, and they're not gonna do any of that because they either don't remember that you're supposed to do that, or they just don't want to do it, so they just skip it completely. But again, as your calculus teacher, I can't do that. So we need to actually verify that that is the location of a minimum. Now I can see that I'm not going to have enough room here, so I'm going to go ahead and erase all of this stuff. I know you probably want me to keep that there, but again, you should already know how to do that stuff. So you saw how to get a common denominator, and now we have to use the first derivative test. So remember, the first derivative test and the second derivative test, they both do the same thing. They test critical numbers to determine if you have a location of a maximum value or minimum value, or in some cases, neither. So we are going to test a prime of x. That's the first derivative. We're going to test it around this point. So what we're going to do is we're going to plug in, well, first of all, we can't plug in anything because we don't know what numbers we're allowed to plug in. We have to figure out the domain first. And figuring out the domain, as we saw in the previous problems, is not something that is exactly obvious in many cases. But x, the smallest value of x, is probably going to be obviously 0, right? You can't go into negative numbers, because we're talking about geometry here. You don't really have negative numbers in geometry. But I'm going to write a parenthesis because x can't be really equal to 0, because then the volume of the box would just, or the surface area would just go to 0. We don't really have that. We're not interested in having a box that has no surface area, right? That would mean it disappears. So now, what is the biggest value of x? Well, this is not going to be exactly obvious. You want to use all the tools that you have to figure this out. Look at your picture, look at your equation, look at this equation maybe, and combine all this stuff to try to figure out what the biggest value of x can be. So we can start making x bigger and bigger and bigger. That means the base of the box just gets bigger and bigger and bigger and bigger. And as the base of the box gets bigger, h has to get smaller and smaller. Because remember, the volume is set in stone. The volume has to be 2,000 cubic centimeters. So we can just make h bigger and bigger and bigger, and actually, theoretically, we could just keep making it as big as we want it to be. I know that sounds kind of weird, but h can look at x over here. X can just get as big as you want it to be, and h will approach 0, but it will never equal 0. You can make x a trillion to the trillionth power, but h is still going to have a value. It's going to be very close to 0, but it's still going to have a value. So I know that's very strange. It is very strange to think about that. That's why finding the domain is not exactly easy with these problems. But the domain is actually 0 to infinity. And of course, you never write a bracket next to an infinity symbol. So now we kind of have an idea of what our domain is. So we're not going to plug in values that are not in the domain now that we have our domain. So let's try some values. So what should we try over here? We can try really anything. We don't really care what the value of a prime is. We just want to know if it's positive or negative. So maybe we can plug in 1. That seems like a pretty easy number. If you plug in 1, you see we obviously have a negative number. So over here, what can we plug in? Well, you could probably plug in maybe 100 or 1,000 or whatever, and it's going to turn out that that's always going to give us a positive derivative. Now, I'm not going to actually plug those numbers into this and show you all that, because that would just take forever, and you'd have to write it out, and we would need twice as much space on the page, and it would just go on forever. But all we're doing is just plugging in values to the left of 12.6. We plugged in 1, and we saw that the sign of the derivative was negative. Then we plugged in a number over here. We tried 1,000 or something, and we plugged it in, and we saw obviously that the sign of the derivative was positive. Because if you have a number that you plug in here that's really big and multiply by 4, you subtract 8,000, you're going to get a positive number, because this number is going to be bigger than 8,000. So if that confuses you, you can go ahead and just plug in the numbers and use your calculator and figure that out for yourself. But again, writing that out is just going to take way too much time. Okay, so now we can use the first derivative test. So notice that the sign of the derivative changed from negative to positive. So what that means is that you have something like this. I don't know exactly what the function is going to look like. It'll probably look something like this. I don't really know. I'm just speculating. And so the slope of the tangent line is going to be negative over here, but then as you go over here, the slope of the tangent line is going to be positive. Why is the slope of the tangent line negative over here? Well, because the line is going down from left to right. So the y values of the graph are getting smaller, so that means that the slope has to be negative. So whenever the graph is going down from left to right, that means that the function is decreasing. We learned that, remember, in previous classes. Over here, the function is increasing from left to right. The y values are getting bigger. That's what it means for a function to decrease or increase. The y values are getting smaller or bigger. So that's why the first derivative test works, is it tells us if we have a maximum or minimum, and you can see obviously we have a minimum. Now, we don't need to check the endpoints because there actually are no endpoints. At least, I mean, we do have a 0 here, but as you can see, when you look at that graph, it's not a closed interval. You only check the endpoints if you have a closed interval. Now, we did have a partially closed interval in some of these other problems, but we didn't need to check the endpoints because we knew that we had a parabola. You know, if you have a parabola that looks like this, you don't need to check this point to make sure that the y value is smaller than this point up here. It's just a waste of time, right? We already know that. So, so we know that we have a minimum value because of this sign change here. And because we consider the domain and we see what's happening, we know that we don't have to check any endpoints to make sure that those points are not minimums. For example, you might have something like this. This could be maybe 12.6, but if you have a closed interval where you have pink points on the side there, well, actually, that's the minimum value, not this. So that's why you have to check the endpoints. But again, here we don't need to check the endpoints because it's not a closed interval. You have parentheses as opposed to brackets. So again, this is why students don't want to do this stuff, is because it just takes forever to do all this stuff. But again, because I'm your teacher, I have to do it. You know, you're not allowed to just assume that this is the location of a minimum value. Now, this problem asks us to find the dimensions of the box that will minimize the cost of the materials. It doesn't say to find the minimum surface area. All right? It doesn't say to find the minimum surface area. It says to find the dimensions of the box that will minimize the cost of the materials used. So we need to find x that will minimize the cost, which we already did. That's going to be roughly 12.6. But we also need to find h. So h is given by this green expression up here, right? So the length is approximately 12.6, because remember, look at your picture up there. The length is x, right? The width is also x, so the width is also going to be 12.6. And now h, let's look at h. H is going to be 2,000 over x squared. So I'm going to write that over here. 2,000 over x squared, but x is going to be 12.6. And if you do that, we get 12.6. So isn't that interesting that those should be squiggly equal signs. The height that will produce the minimum surface area is a height that's the same as the length and the width. Also, I forgot to write my centimeters. We have centimeters here, and so that's it. Those are the answers that we're looking for. All right. So we have the dimensions of the box that will produce the minimum surface area. Okay, so let's try one more of those. So it says here, a manufacturer must design a cylindrical container with a volume of 1,500 cubic inches. Find the dimensions of the container that would minimize the amount of material necessary. Okay, so step number one, we have to draw a picture. So it's a cylinder. So we're concerned about the radius. Whenever you have a cylinder, you're always concerned about the height and the radius. So now we need to find an expression of the thing that we're trying to minimize. We're trying to minimize the amount of material used again. So what that means is we want to minimize the area, the surface area. So the surface area, now this is something where you need a formula. You need to go online or, wherever you can find the surface area formula. We have, remember, the area of a circle is pi r squared. Well, we have two circles, a circle on top and a circle on the bottom, so we need two of those for 2 pi r squared. Now, if you unravel this cylinder, let's say that you cut the cylinder down the side like this, and you unravel it. I guess the tops would have to be, cut off somehow. But if you cut it down the side like that and unravel it, then the length, this side, well, first of all, the height, or I should say the length here is going to be h. But what is this length going to be? Well, remember, if you want to find this purple length, that is the length all the way around the circle. But that's the circumference of the circle. Circumference is 2 pi r. So if you unravel it, you get this big old rectangle. And obviously the area of a rectangle is length times width. So now most students are not really required to remember that. You'll be given a formula. I'm not going to require you to remember that. So if you didn't understand that, that's okay. But that's where that formula comes from. So now we have a problem. We have too many variables. So we need to go to other information. And of course, the other information is that. So the volume of a cylinder is pi r squared h. So this is the volume of a circle, and then you multiply that by the third dimension to get your volume. Again, you can just find this formula online, but I'm going to give you these formulas for the next problems you're going to do. So 1500 is the volume, and this gives us an equation that we can use to get this side in terms of only one variable. So h is equal to 1500 over pi r squared. Now you might wonder, why is it that I solve for h? Why don't I solve for r? Well, you could solve for r, but that would make things more difficult because r is squared. So now I'm going to plug in h. So we have 1500. So the pi's are going to cancel out, one of the r's are going to cancel out, and you're going to be left with 3000 over r, it looks like. So a very similar equation to what we had before. So I'm going to change that to function notation. So we're done with step number 2. Now on to step number 3. We're going to find the derivative of that function. But before we do that, we're going to change the form to make things easier for us when we find the derivative. So I changed this expression there into 3000 times r to the -1 power. Again, you don't have to do it that way. You can just use the quotient rule if you want to, but most students prefer to do it this way. So now we can find the derivative. And it's important to understand that pi is just a constant. It's not a variable, so you don't have to use the product rule. This whole purple stuff here is just a constant. Alright, very important to understand that. And I'm going to find the derivative here, and I get the following. And now I'm going to change it to something that makes sense. So there you go, there's the derivative, but we're going to get a common denominator and put everything into one term. And the reason we do this is we want to see what the critical numbers are we may miss some critical numbers if we don't combine everything to one expression or one fraction. So I think we're ready to go on to step number 4. And I'm going to copy this and paste up there for number 4. Number 4 is to find the critical numbers of our function, and that's where the derivative is undefined or 0. So if the derivative is undefined, that means the denominator has to be 0. And if the derivative is 0, then obviously that would mean the numerator would have to be 0 and the denominator would not be 0. If the numerator and the denominator is 0, that means it's that's a different situation, but we want to know just when the numerator is 0. So setting the numerator equal to 0, if we solve for r, over here we get 0, of course. If we solve for r over here, then r is equal to the cube root of 3000 over 4 pi. Sorry, that's kind of written small there. And again, you don't have to write a plus or minus symbol because our blue index is an odd number. So we don't really care about this critical number because that's not really in the domain. R is not going to be 0 because then we wouldn't have any volume at all. But we are going to calculate this orange value here. So 3000 divided by 4 pi. That's going to give us 238.7, and then cube root that, and we get 6.203. So R is approximately 6.203. We can just say 6.2, that's good enough. And that's going to be inches. So now we can't just assume that this is the location of a minimum value. We have to use the first derivative test to check it. And before we start plugging in values, we have to figure out what values we're allowed to even plug in. So we look to the domain for that. R can't just be any number. So what are the possible values of R? Well, you can see with this equation, if you compare the equation for height and the equation for area and the actual figure itself, you can see R can actually be any positive number. It can't be 0 because that would make this this pink expression undefined. But it can be any positive number that's greater than 0. I mean, R doesn't really have an upper bound. As R gets bigger and bigger, H gets smaller and smaller, but H can just keep getting smaller and smaller and smaller and smaller. There's no limit to how small it can get, as long as it's a positive number. As R gets bigger and bigger, H approaches 0, but it just keeps approaching. So the domain, and I know that that's kind of difficult to consider. I understand that. It is very difficult to consider that. That's what calculus is all about, is considering how you can get infinitesimally close to something and just keep getting closer and closer and closer. But now that we have the domain, we're going to check this pink critical number. And the way that we do that is we plug in some values over here. So we can plug in maybe 1 into the derivative. So if we plug in 1 up here, we see that we get a negative value. And if we plug in maybe 10 up here, or we can plug in any number, we can plug in 1,000, we can see that that's definitely going to give us a positive value for our derivative. So we're calculating the sign of the derivative when we plug in these numbers. And so now, because the derivative changes from negative to positive, we see that this is actually the location of a minimum value. So says we want to find the dimensions of the container that would minimize the amount of material necessary. So we have the radius, now we just have to find the height. So the height is approximately equal to that green thing up there. If R is 6.2. And so if we do this in our calculator, we get, let's see, we get 12.42, so it ends up being exactly double the radius. So the radius is 6.2 inches and the height is approximately 12.42 inches. So that's the answer. Okay, so I want you to take a picture of number 5, and I'm going to leave number 6 in the window, and I want you to try number 7. Now, again, this stuff is pretty challenging, so if you get stuck, that's okay. Go back and use your screenshot of number 5 to help you. These problems are really involved, so just give it your best shot. Try your best, and I need you to give an honest attempt here. So I know these problems can be overwhelming, but you still need to know how to do these. So try number 7, and I want you to be aware that it says here in green, it says the left and the right sides of the box must be squares. So in the problem number 5, it said the base of the box had to be a square, which assumed that obviously the top of the box was a square. But now it's saying the left and right sides of the box must be squares, so that's a little bit different. So keep that in mind. So also, you see up here we have our formulas. So you have the formula of the surface area of a rectangular prism and the formula for the volume of a rectangular prism. So try number 7. When you come back, we'll do it together. Okay, we're back. If you got that right, very good. Now, I know what you're thinking. You're thinking, a lot of students don't use the first derivative test and they don't consider the domain, so can I just skip that? Well, you probably should not skip it. I'm not going to require that you show that when it comes to your answer. Well, obviously when you check your answer, I'm not going to do that stuff. I'm just going to give you the answer, but you should probably check that the critical number is really a location of a maximum or minimum. You need to get in the habit of doing that. And you need to practice your first derivative test. And you also need to practice finding the domain of a function. So these are all things that you should do. So again, if you got that right, good job. I want you to get a picture, if you haven't already, of number 5. And get a picture of number 6 and 7. And now I want you to try number 8. You've got your formulas up there. When you come back, we'll do it together. Alright, we're back. 11.5176 inches. So notice that the height, again, just happens to be about double the radius. So I know that this is a very similar problem, almost the exact same problem that we already did, but again, I'm purposely doing problems that are the same over and over again so you can get a feel for how the methods work. So I don't want to just throw you into the deep end and give you problems where you have to figure everything out on your own. You're capable of doing that, but we're trying to start off easy here because these are very difficult problems. So if you got those answers right, good job. Now we don't have much time left, but I want to give you just one more type of problem. This is where we're going to be maximizing volume, and we're not going to have time to get all these problems done because I don't want to make you go more than 2 hours here. But it says here a box with a square base must be produced. Its surface area must be 76 square inches. So now we're given the surface area, not the volume. Find the dimensions of the box that will produce a maximum volume. So again, we're maximizing volume, not surface area. Find the maximum volume. So we have to find the dimensions of the box that will maximize the volume, but we also have to actually find the maximum volume. So you have to be very careful that you follow the directions completely. You don't want to lose points because you're not answering what the question is asking. So we have a box with a square base, so we can draw a figure similar to what we already drew. Square base, the height is, we'll just call it h, so that's the picture. We're trying to maximize the volume now, so the volume of a rectangular prism is LWH. Now we know that the length and the width are the same, so we can change that to x squared times h. But we have two variables on the right side of the equation. We're not allowed to have that, so we need to use the surface area formula. The surface area of a rectangular prism is some variation of this. I'm not writing it exactly the way we wrote it before, but it doesn't really matter because of the commutative rule of multiplication and the commutative rule of addition. So the area is equal to 2 times the length times the height plus 2 times the length times the width plus 2 times the width times the height. And of course that gives us our familiar expression 2x squared plus 4xh. Okay, so what that does is it gives us an expression. Well, first of all, we need to plug in A is going to be 76. So I got that from there. And we're going to solve for h. So we have 76 minus 2x squared over 4x. You want to simplify that if you can. And so I think we can a little bit. I think I'm going to try to separate that into 2 fractions. And 76 divided by 4 is 19. So it looks like we have 19 over x minus x over 2. So 19 over x minus x over 2. So now we can plug that in for the height. We have x squared times 19 over x minus x over 2. Okay, so let's distribute. You might wonder if we could just find the derivative in this form. We could, but we'd have to use the product rule and all kinds of other stuff. So we have 19x minus 1/2 x squared. You might write this in a slightly different form, but that's okay. Whoops, that should be x cubed. Okay, so now we're done with step 2. Again, step 2 is often the most difficult step. So now we want to find the derivative, and we don't have to do anything special before we find the derivative because this is fairly easy. We get 3/2 x squared. Okay, and then on to step 4. We're going to find the critical numbers, and the critical numbers are what makes the volume, or what makes the derivative either 0 or undefined. Now there's no x values that make this expression undefined, so we can just set it equal to 0 and then solve, and we get plus or minus the square root of 38 over 3. So let's estimate that. So you can get your calculator out. That's about 3.559. So x is approximately equal to 3.559. Now, why did I not write plus or minus here? Well, because obviously x cannot be a negative number, so we don't really care about that. That's not part of the domain. And that would be inches. So again, we can't just assume that that's the location of a maximum value. We have to use the first derivative test. Again, most students would just skip this and say, well, I'm not going to do that, I don't have time. But as your calculus teacher, I can't do that because technically you do have to check. It is conceivable that you might get a problem where a teacher might try to fool you and give you a number that's not even in the domain. I don't think that happens very often, but they might give you a number that's not in the domain of the function, or they might give you a number that is neither a maximum nor a minimum, or a number that turns out to be a minimum and not a maximum. So you have to use the first derivative test. And in order to use that test, we have to plug in values, but we can't do that unless we know what the values are that we can plug in. And if you compare this equation, and this figure, we can try to find the domain. So obviously 0 is the smallest value of x. X cannot be 0 because then the box would just disappear. So we'll write a parenthesis there. Now what is the biggest value of x? Well, it's not exactly easy to see, but there is an upper bound. And the best way to see the upper bound is to graph this purple function. And to use your graphing calculator to actually find the x-intercept, it's kind of complicated finding that upper bound. I mean, it's not that complicated, but it's just one extra thing that you have to do that we don't really want to do, but we have to if you want to find the domain. Again, this is one of the reasons that students they don't find the domain, they just forget about it. But if you were to graph that purple function, you would have 6 over here, and your graph would look something like this. And obviously this is the maximum, but the reason that we have an upper bound is because you can see that the volume actually becomes negative down here. You can't have negative volume. So the big question is, how do we know this orange number to put there for the upper bound? And we would have to do some math in order to figure out that number, or you could just use your graphing calculator. So in order to actually do the math, you would have to set the volume. Basically, you just find the x-intercepts of this graph. So set this volume equal to 0 and solve for x. So if you did that, you would get the following. So if you wanted to solve for x, you would have to factor out an x, and then you could set, obviously 0 is the one of the intercepts. I didn't draw that graph very well, but it should be going through 0, something like that. So x equals 0 is one of the intercepts, but the other intercept is given by setting this equal to 0. So I'm not going to do that because it's just going to take too much time. But I will solve that in my calculator, so you can see what that number is. Looks like it's going to be 6.16. Roughly, and we'll just highlight that. So again, that's why this stuff is considered to be so involved, is because you're expected to find these numbers if you do the math correctly. And the big question is, could you get away with not finding the domain and not using the first derivative test? To be honest, you'd probably have a few points taken off on your in school if you didn't do this stuff. So anyway, let's plug in so this is our domain. Let's plug in 1, and if we plug in 1, we get a positive number. So we're plugging in this to the derivative. Let's plug in 5, and if you plug in 5 and calculate, you see that we get a negative number. So notice that the sign of the derivative changed from positive to negative. So remember, the first derivative test tells us that indicates that that's the location of a maximum value. Okay, so this problem asks for the dimensions of the box that will produce the maximum volume. So the length is going to be approximately equal to 3.559, and that is inches. The width is going to be approximately equal to 3.559 inches. And the height, we have not found the height yet, but we can do that here. Height is equal to 19 over 3.559 minus 3.559 over 2, so whatever that equals. So 19 divided by 3.559 minus 3.559 divided by 2 is equal to 3.559. So it just turns out that it's equal. Again, that's an interesting result there, that the dimensions tend to be equal. But that's not the only thing that we're supposed to do. So we found the dimensions of the box that produce the maximum volume, but we also have to do the orange part there, find the maximum volume. We haven't done that yet, but that's pretty easy. all we have to do is we just have to plug in that number 3.559 into the purple formula up there. So 19 times 3.559 minus 1/2 times 3.559 cubed. And we should have squiggly equal signs because we plugged in a rounded off number. So let's go ahead and calculate this. And I'm doing that in my calculator. And we get 45.08. We can just put 45, that's good enough. Cubic inches. Okay, so that's the orange part that we found there, and let me rectangle this pink because that's part of our answer. And now that I think about it, when you do this, you really should say which part that we found. So this is part A, this is part B, just to be thorough there. Okay, so we have one more problem. I'm sorry that this class is going kind of long, but you can see that these problems are difficult. So I want you to try number 10. I'm going to keep number 9 in the window. So go ahead and try number 10. When you come back, we'll do it together. Okay, we're back. And it looks like we get approximately 217. We're estimating anyway, so it's probably best to just leave it like 217. That's fine. The problem doesn't tell us what to round off to, so that's fine. And that's going to be cubic centimeters. So again, there's a lot of types of varieties of these problems that we could do, but we just don't have time to do every variety of these problems. There's not enough time in the class. So we're going to do another class on optimization problems, but even then we're still not going to have time to do every single type of problem that you could see when it comes to these optimization problems. But you're not really required to know every single type, nor is it even possible to know every single type of problem that you could see. We're just going to do, maybe 3-4 other types of problems and go on to the next part of the course. There may be an optimization problem on the advanced placement exam, but it's not going to have a lot of complex algebra, most likely, and so it's not going to be something that's going to really take that long. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and screenshot number 2 and number 3 and number 4 and number 5 and number 6. But don't go before you get your homework. Remember, the homework is not optional. If you don't do the homework, you're going to learn absolutely nothing in this entire course. So get a screenshot of this first or the first 2 pages and screenshot number 2 and screenshot number 3, but don't go before you get the answers. Remember, it's not enough just to attempt the homework, it must be done correctly. So here's the answers to the homework. If you get the wrong answer, go back and figure out what you did wrong and fix it. So get that homework done, and I'll look forward to seeing you in the next class.